Hello everyone, in this problem we are given an array and we are allowed to choose any element and flip a bit in its binary representation. And we have to find the minimum number of such operations required to make the bitwise XOR of all the elements equal to k. Let's understand this with the help of an example. So we have represented all the numbers in the array with their binary representations, and this is the binary representation of the value of k. Here we have to XOR all these three to get the value of k. For the rightmost bit, we see that 0 and 0 will cancel out and 1 will cancel out in the XOR operations. So the rightmost bit will be 0. Similarly, for this bit, we see that 1 will cancel out and 0 will cancel out. So this bit will also be 0. And for the leftmost bit, we see that 0 and 0 will cancel out, but these two will give an XOR of 1. Our desired binary representation is this. We see that this is matching, but these two are not matching. So we'll have to flip some bits over here to make them equal. Over here, we need an output of 1, so our bits must not cancel out. So let's say if we flip this bit to 1, then these two will cancel out, but the output of these two will be 1. So one flip is okay for this. Similarly, for this place, we need an output of 0, so all our bits must cancel out. We see that these two are cancelling out, but let's say if we make this to 1, then these two will also cancel out. So one flip is required over here, and in total we need 2 flips. For the second example, we see that the XOR of the array should result in 0. We see that these two numbers are equal, so their XOR will also be 0. Similarly, these two are equal and their XOR will be 0. So overall, for this array, if we XOR all the numbers, it will result in 0. So we do not require any flips. Let's try to come up with an intuitive solution using this example. Let's try to understand first what we actually mean when we desire a bit of 0 in the output k. What this actually means is when we XOR this array, we are going to XOR this corresponding bit, and this XOR should result in 0. So this means that the pair of the bits should cancel out and result in 0. We know that 2 bits cancel out when they are equal. This is also possible when they are both 1. So let's suppose all the bits are zeros. So these two will cancel out and these two will cancel out, and the final XOR will also be 0. So we don't need any flip over here. So now let's consider when we have one bit as 1 and the remaining 3 bits are zeros. Over here these two will cancel out, but these two will not cancel out. So we'll either need to flip one of these bits to get an output of 0. Now let's see when we have 2 1s and 2 zeros. We see that these two will cancel out and these two will cancel out. So we don't require any flip. Now let's take the case when we have 3 1s. These two will cancel out, but these two won't. So we'll have to flip one of these bits to make them 0. And finally, when we see that we have 4 1s, these two will cancel out and these two will cancel out. So we will not require any flips. So there is one observation that you can make is that whenever we have an odd number of 1s, the XOR of all the bits will be 1. This will also be true when we have an odd number of elements, because the XOR of 0 will be 0, and whenever we have an odd number of 1 bit, the XOR will always be 1. So whenever we require a 0 at a particular bit, if we have an even number of 1s, that means all the 1s will cancel out and the XOR will result in 0. So no flips will be required. And similarly, when we have an odd number of 1s, one of the 1 will remain after XOR. Hence we'll have to flip it to make it 0. Similarly, when we look at the output bit of 1, we want an odd 1 remaining after an XOR. So that means when we have an odd number of 1s, we will require no flips. And correspondingly, when we have an even number of 1s, that means all the 1s will get cancelled out. And since we require 1 at the output, we'll have to flip one of the bits. Hence to solve this problem, for each position, we can calculate the number of 1s. And then we can compare it with the corresponding bit on k and check if we require a flip or not. One question you might be having is for how many bits we have to count the number of 1s. To answer this, I have already explained in one of my previous videos how 32 should be enough for most Leetcode problems. You can check that out over here. So in general, you can keep a count till 32 bits and that should be sufficient. The time complexity of this solution would be O of n because we have to go through the array only once. And the space complexity would be constant because we have to store the number of 1s for only 32 bits. Let's implement our solution. The first thing that we'll do is initialize a hash map to store the count of ones for each bit. And now we'll go through each number in the array. And for each of the 32 bits, we are going to check if it is set or not. So if it is set, we are going to increment the count of 1 for that bit by 1. Here we are finding the ith bit for an integer and then we are ending it with 1. So if this is 1, we are incrementing 1 to our count. Now we'll initialize our onset to 0. And now we'll go through each of the 32 bits. And for each bit, we are going to find the ith bit if it is set in k. So we are going to do the same thing, right shifting it by I and then ending it with 1. Now we'll handle the first case when the kth bit is set. It means that if we have an even number of ones, that means the XOR will not result in 1. So we'll have to increment the count of our flips by 1. And if the kth bit is not set, it means we require an even number of ones. So if we have an odd number of ones, in that case we'll have to increment the count of flips by 1. And once we have done this for all the bits, we can return our result. We are now done with our solution. If you have any doubts or concerns regarding this solution, please mention in the comments. If this video was helpful, please leave a like and subscribe to the channel for more such content. Thank you for watching and see you soon.